Welcome, everyone, back to my science channel. I'm Franklin Hu, and today I'm going to be responding to Draft Science. So he's been making some response videos, and so I thought I'd return the favor by responding to his question about uh, kinetic energy. So uh, I think this all started with this video that I have up here, which explains his main problem with it. So let's just listen to that for a little bit here.
All right, quick rundown on what I think is the most obvious and most catastrophic and biggest mistake of science ever. The MV versus 1/2 MV squared controversy, kinetic energy versus momentum. It started in 1650 with 53, 57 with Leibniz, who was basically saying to Descartes and Newton that you're.
So draft science, draft physics has been going on about this for quite some time. And it's interesting to see that he's done some actual experiments and things like that. So I congratulate him for that, because you should never believe anything just because someone says it. And I haven't done my own experiments in, say, investigating the conservation of momentum and things like that. So good for draft science. But I've just been ignoring this because it's like, kinetic energy equals 1/2 mv squared. I would have thought that this is within one of the realm of the settled science things, right? It's like, um, but actually, I mean, it will turn out that I'm gonna have to agree with that the proper expression of kinetic energy is in fact mv and not 1/2 mv squared. But let me show you how I got to that. But first of all, let's look at what he's got on his board here. Uh, Now, I'm not so sure about the whole weight thing, but definitely there's an experiment that, like, by Walter Lewin, that he's been pointing out. And he's got here on the board here, he's saying there's like 100 m does not equal 166 m. And he's saying that, this is like a free energy device thing, that the energy is not being conserved in this case. So I took a look at that, and I made my own calculations. So this is done on an air track, and you have a 1 meter weight hitting a 1 kilogram weight hitting a 2 kilogram weight, and what happens is that it collides, and it causes the other original weight to go back a little bit, and the other weight to go forward. So, and Draft Physics has done their own experiment on that, which I thought was pretty good. Um, but what I did was that made my own calculations of what 1/2 mv squared is. And so I came up with, it's 1/2 times 1 kilogram times 1 meter per second. I mean, I'm presuming that the weight is coming in at 1 meter per second. And so the answer is 0.5, and that should be in joules, zero point 0.5 joules. And then I did that for the after reaction, which is, you've got this 2 kilogram object, and it's going at 2/3, or 0.666 meters per second. And you've got the original one going at 1 meter per second, which is, you know, 0.333 squared. And so that is equal to 0.444 plus 0.005 equals 0.4999, which is, it's the same. It's 0.5, right? You round it up. So from the kinetic energy standpoint, assuming that those are the correct measurements, I mean, that's why he's measuring it, because he simply doesn't believe the demonstration that was given in the MIT Walter Lewin, thing. So, but assuming that was true, uh, it's not the energy appears to be conserved. Okay, but that's not the calculation he's actually making over here in his board over here. So somehow he comes up with 100, m, whatever the heck those are, does not equal 166 m. So the only thing I could figure is that he must be doing that calculation since he's doing the MV calculation, kinetic energy as just momentum. So if you are starting with the velocity of 100 meters per second, then you would say that the m times v would be 100 times 1 kilogram. So that's where you could get the 100 value from. And I don't know what the m means, but it should be in joules. Kinetic energy should be expressed in joules. And so you do that calculation, and of course the incoming is 100 times 1 kilogram, so you get 100 joules. And then you do the same calculation just like we did above. You got the 2 kilograms times the 2/3, so 2/3 of 100 is 66.66. So you get 133, and then you get the other original weight going at 1/3 the velocity. So 1/3 of 100 is 33. And so you add those things up, and yeah, that's 166, right? So, the same thing we did up here, but down here, right? So those things certainly don't seem even. It's like the momentum, which is what MV is typically stated as, is not conserved, right? It's like, how can you get you know, more momentum out of the system than you originally had? But a little research showed that momentum is a vector, which means it has a particular direction, right? So it may be that you just can't, add these things together to be 166, because since the other vector is going in the opposite direction, maybe what you really need to do is to subtract it. So 133 minus 30, we get back the 100 that we had originally. Now, to me, that seems a little sketch, but it's not completely unreasonable that a momentum is conserved because we've got objects going in the opposite direction. But actually, that really didn't convince me at all. That what's because both of them seem to more or less come up with the right answer. But what did convince me is that I had remembered. I thought I had a derivation for the kinetic energy formula that was pretty convincing to myself. So I went searching on the internet, looking for various things like if you say derive 1/2 mv squared, you put that in there, and then you start seeing a bunch of I don't know, weird derivations about how this is done. So, and at some point, the v squared just magically appears. It's like, well, where did that come from? Because that's the key. I mean, the key is, where did these twos come from, and where did these v squares come from? And in all these derivations, they just, I don't know, they just seem to pop out of nowhere. And it's like you lost me at the very first step of what you were doing here, right? So it's just not terribly convincing, where these things come from. So, but I remembered something about rockets and how they act. So let's say you have a 1 kilogram weight, and you put like a little rocket motor on it, and that rocket motor expends a certain amount of energy per time. So let's glue our rocket motor onto our 1 kilogram block on our air track and just light that sucker up. And after 1 second, it'll be going at some certain velocity, right? So the thing is that if we can do that, then we can calculate, how much energy came out of the rocket, and that darn well better be equal to the amount of kinetic energy that object would have at that velocity, right? So question is, how do we do that to make sure? So I was going to do this. I was going to prove this, that it was 1/2 mv squared, by basically checking it, right? That I know if I put in X amount of energy into the rocket, that when it hits that velocity, or it if it hit the wall at that point, that the amount of energy it would actually have to equal the amount of energy that was put in, right? That would only make sense, right? but not so much. Okay, let me bring up my notes on this. So let's do that. So let's suppose that we have a rocket and it is has a 10 Newton thrust, and we're gonna let it go on the track for 1 meter with a 1 kilogram mass. Okay, now that would seem to be rather confusing, but the amount of work, see, so that is defined as work, and this is expressed in joules, is the force in newtons times the distance in meters, right? So in this case, we would expect there to be 10 joules to be expressed if I fired a 10 Newton rocket and I let it do its thing over 1 meter, right? That's how it works. And I'm saying that since we can calculate this kinetic energy, that better be equal to the amount of energy done to create the velocity. So now we have to define a few other terms like, okay, what the heck is a Newton, right? So a Newton is the force required to accelerate 1 kilogram to 1 meter per second. And this is an acceleration. So after the first second, the object would reach 1 meter per second. And at the second, it would be at 2 meters per second. And at the third second, it would be at 3 meters per second. So if we know the amount of time that's been able to pass, we can calculate exactly what the instantaneous velocity will be at any given time segment, assuming there was only 1 Newton of force there. So, but I'm going to simplify things. We're just going to stick with, let's just do 1 Newton of force, right? So if I had a 1 Newton rocket and I let it go for 1 meter, and that's easy to imagine, nothing tricky about that, no matter how much time it takes, that is equal to the work of 1 joule, right? So we have a measurement of energy, 1 joule. And that fact, this is how the joule is defined. It's the work done by moving 1 Newton, applying 1 Newton over 1 meter for, I believe, a kilogram. Okay, so the velocity of that rocket will be 1 meter per second after 1 second. So we know what the terminal velocity is after 1 second. It's going to be 1 meter per second. So if we plug that in as 1/2 times the mass, which is 1 kilogram, times the velocity, which is going to be 1 meter per second, we get out half a joule, right? So this is our first sign that this is not right, because we determined that the amount of energy that if I had a rocket sled of 1 kilogram and I let it go for 1 second over a meter, that's equal to 1 joule. But the kinetic energy is saying that it's half a joule. That's like half, right? That's not right. Okay, let's go ahead and make it a little more complicated. Let's go ahead with the 10 Newton example again. So in this example, the velocity after 1 second would be 10 meters per second. And so we once again plug in things. So 1/2 times 1 kilogram times 10 meters per second. That's the instantaneous velocity it would reach after 1 second. And we get 50 joules. Okay, that once again, this is not right. We put in 10 newtons over 1 meter, should be 10 joules. But, we get 50 joules. So that's not quite right. Although I am thinking that, let's see here, can we determine that it's only traveled 1 meter? Perhaps that is the problem, that we need to determine the total distance that this thing travels. Maybe that might be the problem here. So maybe I may have helped solve a problem because we have this problem with the work is calculated by newtons over distance. And I'm presuming that after 1 second, it would only be able to get 1 meter, which is probably not the case. If you're going 10 meters per second acceleration, you're probably further than 1 meter. So that would be a problem. So maybe these calculations are not exactly accurate. But the thing that kind of convinced me that maybe it was is that if you actually do it in those terms, like the kinetic energy is just m times v. So in this case, we have an example where we have a 2 kilogram, a ten Newton rocket firing over 2 meters on a 2 kilogram mass. So you would think that the power expended is 20 joules. And if you look at the m times v, you would see that that equals, right, 20 joules. Or if you did something really complicated, like you did 13 newtons over 5 meters on a 3 kilogram mass, that should be 65 joules. And we were figuring the velocity at 4.33 meters per second acceleration. You would get 699 joules, which would greatly overstate the energy by 10 times. But if you just did mass times the acceleration, you get exactly the original number of joules. So in this case, it seems that the kinetic energy formula should be mv and not 1/2 mv squared. But just as I'm talking to you here, I have discovered possibly the problem, which is that work is always the force over the actual distance traveled. And in this case, it's probably more than 5 meters. So that this probably increases this figure here. So let me go figure that out, and I'll get right back to you.